Okay, so since our mics are hot right now, for those of you who may be watching this program and you're on explorescientific.com/live, you'll see that there are social media channels that you can click on, and we're broadcasting to all of them. So if you'd like to chat with us, you'll just click on one of those. So it could be Facebook, could be YouTube, could be Twitch, could be Twitter, but you'll see it down on the page. And our regular viewers right now, of course, know how to navigate all of this. And sometimes they even switch from channel to channel, depending on which one's streaming better. So sometimes they're, that's the way it is. But it's going to be exciting to have this new program, 7 Months of Science. And I know that Caitlin and Paul, who are joining us today, are very excited about it as well. So hang in there, and we'll get started here in a couple of minutes.
After its discovery in 1999, our first hints of what asteroid bending looked like came from the Arecibo Observatory. Then, as the OSIRIS-REx spacecraft made its way to Bennu, the asteroid grew in detail from a few tiny pixels to a surprisingly rugged world, littered with giant boulders. OSIRIS-REx arrived at the asteroid on December 3, 2018, and began surveying Bennu for the years leading up to the touch-and-go sample collection event. The spacecraft discovered boulders the size of buildings, and imaged the surface down to 5 cm per pixel resolution. While observing Bennu, we made some unexpected discoveries. OSIRIS-REx spotted pieces of rocky ejecta bursting off Bennu and into space. The spacecraft was able to observe the entire life cycle of a natural satellite, ejecting off an object, entering into orbit, and returning back to the surface. OSIRIS-REx caught a glimpse of a black hole 30,000 light-years away. The discovery was made by an instrument about the size of a shoebox called REXIS, the Regolith X-ray Imaging Spectrometer. It detected X-rays radiating from a point off the asteroid's edge. OSIRIS-REx has imaged Bennu better than we have Earth and our own moon. Using this extremely high-resolution data, we've been able to create stunning visualizations of the surface of the asteroid. We used imagery from the Nightingale sample site to create a 360 VR visualization of the rugged terrain. Using an extensive catalog of surface imagery, OSIRIS-REx navigated itself autonomously down to the surface for sample collection. It used software called Natural Feature Tracking to match up landmarks with its catalog to ensure it was on the right track. Approximately 200 million miles away from Earth, the spacecraft performed a series of burns to navigate itself the rocky surface. At 6:08 p.m. Eastern on October 20th, 2020, OSIRIS-REx successfully tagged sample site Nightingale within 1 meter of its targeted location. The onboard cameras captured incredible footage of the touch-and-go sample acquisition mechanism, TagSam, contacting the surface. Imagery from SAMCAM showed rocks and dust overflowing from the TagSam edge. The team is confident they've exceeded the mission requirement of collecting at least 60 grams of material. And on October 29, 2020, they stowed the sample for return to Earth. OSIRIS-REx imaged Bennu for the last time on April 7, 2021, and will depart the asteroid on May 10th on its 2-year journey to deliver the sample to Earth.
Well, let's see here. Where's my video here? Here we go. Well, good afternoon, everybody. Good evening. This is, of course, Scott Roberts here with Explore Scientific, and I'm joined by our lead host here, Caitlin Ahrens. She is a postdoc at NASA Goddard Space Flight Center, right? But she studied here in Arkansas, and that's near and dear to my heart, of course. And joining us is Paul Knightley. Paul is a scientist, researcher, a professor, is that right?
Graduate student.
Graduate student, okay. Soon to be professor, okay.
Yes.
And he has spent, I don't know much of the details of this. I'm quite excited to learn more. But he's spent a period of time, I think an extended period of time, in a simulation of a Martian habitat. And so you're the only guy that I've known that has done something like that. So I think that's very cool. Caitlin, I'm going to let you take it from here and let you introduce Paul further, and then Paul, you have a video that you'd like for me to share as well, so I'll do that, okay? So here we go. And it's all yours, Caitlin.
All right, well, thank you everyone for joining us for the 7 months of science part 1. So I'm so excited that Paul can join us for our very first segment of the 7 months of science segments series. So what's really wonderful about Paul is that Paul and I have known each other for a couple years now, and so whenever he ventured off to the Canadian wilderness, essentially, he will certainly give more details of the undisclosed location in Canada of his adventures. it was so astounding that I was so excited, like, oh, I actually know someone who's done this now. And to have a friendship with someone like that who's done that kind of an amazing adventure, it's like, oh, awesome. So excited that Paul can join us and to expound upon his adventures of a simulated Mars adventure. So take it away, Paul, and with your video that you'd like to show us.
Yeah, absolutely. Thanks for the introduction. So yeah, I'll go ahead and have Scott cue up the video first. This is just kind of a 2-minute video summary of what I'll talk about during my presentation, but just kind of help set the stage and provide some nice visuals for the mission before I launch into my talk.
Okay, that sounds fine. All right, so here we go.
Now on the top of the hill of Vikings. Over.
Let's take that full screen. There we go.
The Mars 160 objective, to conduct twin studies in both the desert and the Arctic under Mars-like conditions, is the first of its kind among Mars analog research and includes a multinational crew of 8 men and women representing 8 countries from around the world.
Handcom. Do you receive us? We receive you. That's good to hear. We're right outside.
The crew is documenting the presence of lichens, a species that is adapted to extreme environments on Earth. It may prove vital in discovering signs of previous life on Mars.
They are very much adapted to live in desiccated areas, high UV radiation. That's why they are relevant for Martian prospector.
Over 4,000 kilometers from the Utah desert and situated on the edge of a 39-million-year-old impact crater, the Flashline Station's uneven terrain and freezing temperatures serve as a constant reminder of the dangers of a real Mars mission.
This is our home. This is our habitat on Mars. If we go outside, you're dead.
There are some people around the world that say we shouldn't send a crew to Mars because it would be too psychologically hard for the crew to handle the situation.
Many of them, they don't understand why we are doing it. They think we're just stuck in a tuna can. So I want to show them that we are actually doing it not just to play around, but for our future.
Since the Mars Society established the FMRS station in 2000 and MDRS in 2001, nearly 200 crews with well over 1,000 crew members have conducted simulated Mars missions, helping to prepare humanity to explore the red planet and our solar system.
Learned a lot about what it takes to plan an expedition, and then once you're actually in simulation, what sort of conditions astronauts would be up against.
Really proud that we achieved so much during this program. If someone wants to send us to Mars, we will be ready for that.
Okay.
Thanks. Yeah, I'll
thank
go
you.
ahead and launch into a presentation from that. So yeah, I guess, first of all, thanks for getting this put together. I'm sharing my screen. There we go. There it is. Okay. So yeah, thanks for putting this together. Really excited to share a little bit more about the Mars 160 simulation. It really was very, probably one of the more unique experiences of my life, certainly may hold true for some time. Yeah, just some of the lessons that we learned from that. So a little bit more about me first. I am a PhD candidate in space and planetary sciences at the University of Arkansas. So we've got the Arkansas crew on tonight. And my research has been focused on using Earth-Mars periglacial analogs, including patterned ground, to better understand buried subsurface ice on Mars. And so most of my research has actually been using drones to accomplish that, but that all was kicked off actually during the course of the Mars 160 mission simulation. So a little bit more about mission simulations in general, just to kind of get us all on the same page about what we're talking about when we say that. So there's actually roughly 24 facilities worldwide that are conducting mission simulations of one form or another. Some of them are specifically focused to Mars. Some of them are a little bit more adaptable and can be used to simulate Martian or lunar settings. And some of them are actually isolation studies that are housed in warehouses. So we've got a couple of different examples here. This is Hera, which is a NASA-run analog, and they can adapt it to any sort of mission type that they're looking to simulate. They've done asteroid missions, Mars missions, and then this is the High Seas facility in Hawaii that has done Martian and lunar mission simulations. And so generally speaking, you can divide mission simulations into a couple of broad categories. There are operational simulations, which are focused on testing the technology and engineering concepts that we would apply on a future mission to the moon or Mars, as well as conducting field research. So understanding how do you design a science campaign to fit within the constraints of a mission to another planet or celestial body. And the other category are human factors studies. These are aiming to figure out what crew composition works best for long duration missions, and also studying the effects of isolation and duration on those crews. Now, typically mission simulation is going to be a combination of those factors, but I think some of the strongest mission simulations are usually just focusing on a handful, especially when you start mixing the operational and human factors components, just so that you can really isolate each of the variables that you're testing. And so in our case, we were primarily a field research operational analog, and we were interested in understanding crew composition and isolation throughout the course of our mission. So what was our mission? So we actually started off as a proposed year-long simulation in the Canadian Arctic, and that ended up morphing into this Mars 160 sim, which we nicknamed the Twin Mars Analog Study. So by design, it was going to be 2 80-day Mars mission simulations, adding up to a total of 160 days. This would be conducted at 2 nearly identical habitats with 2 nearly identical crews at 2 different Mars analog sites that are operated by the Mars Society, with the primary objective being what was the difference in science return between the 2 missions at different analog sites, with the overarching goal of being able to better understand how you can design an effective mission simulation that can be valuable and informative for future mission planning and training. So as the video alluded to, we were a multinational crew. Our crew commander, Alexandre Mongeau, is from France. Yusuke Murakami, our executive officer. John Clark, other geologist on the crew. Anastasia Stepanova, the engineer, and Nusri Srivastava from India. And then the last 3 here on the list, we were kind of the floating crew member, so I was only involved with the Mars Arctic portion of the simulation as a geologist. And then Claude Michel LaRoche was Utah, and Annalie Betty was also Utah. But great group of people. This wasn't a blind simulation. We had all trained together previously. And so that really created a very favorable crew dynamic and really allowed us to actually split up across both of the missions, I think, fairly effectively as well. So great group of people. So I won't elaborate too much on it just because I wasn't in Utah, but the first phase of this was the Mars Desert 80 simulation at the Mars Desert Research Station in Hanksville, Utah. This mission ran for 80 days between September and December of 2016. So coming up on 5 years ago now. A little bit about MDRS. It's actually, I think, one of the longest running and certainly one of the most heavily visited analog research facilities. I think it's coming up on its 20th anniversary this year. They built it in 2001, and it's hosted well over 200 crews. So, and those are crew durations anywhere from a couple of weeks to several months like this one. So really allowing kind of the democratization of mission simulations and allowing a lot of people from different backgrounds to be able to just have this experience and really being able to have people who maybe wouldn't normally do this type of thing and have that be a little bit more accessible to them. So it's a really great facility. Then the twin research station to this was the Flashline Mars Arctic Research Station, or FMRS, which is in the Canadian Arctic. It actually predates MDRS by a year or two, but it's located on Devon Island in Nunavut, Canada, about 75 degrees north, right about where my mouse is where we were located on the island.
Wow.
Has the dubious distinction of being the largest uninhabited island in the world. It's roughly the same size as Iceland for some size comparison. And due to a variety of logistical reasons and just the seasonality being in a very cold and remote part of the world, we ultimately had to scale back the planned course of the mission to about 60 days. And then once all of those logistical issues that I'll go through here in a moment added up, we actually only ended up being there for about 30 days from July to August of 2017, but not before having a really good story to tell after all of that. So to kick things off with that, one, especially since this was really an operational analog to try and better understand how analog missions in general are conducted and how to create one that can really generate the highest scientific return. I really tried to look at it from really a broad brush perspective, that everything that we were doing was basically a part of this broader mission, this broader journey to Mars. So starting with the pre-mission preparation, all of the teleconferences, the workshops, some of the initial training, and going all the way back to the 2014 selection process for all of us as a crew, all fed into just kind of the broader psychology of how does a Mars mission work. And then starting to factor in the logistics. You know, you have your travel getting to an extremely remote site, food and fuel consumption. I mean, these are all factors that are going to play into missions to Mars and our return missions to the moon, hopefully within this decade. So really this all plays into, you know, that broader mission planning perspective. And so we started off, we all flew in from our respective countries, arrived in Yellowknife in the Northwest Territories. We used that as an opportunity as kind of our last bastion of civilization to organize some pre-staged gear, get some additional equipment and food lined up. And this is analogous to, you know, a Mars mission that's going to likely rendezvous with a cargo ship, either en route or at Mars to resupply after a 6 month journey to the red planet. And then, you know, getting ready to spend a year there or up to a year there on some of the earlier missions to explore. And then there's also going to be the inevitable crisis management that you're going to have to deal with. There are going to be things that come up that you can't plan for. In our case, it was a food shortage, which with some of the travel delays that we had, it actually ended up being somewhat beneficial for us. We were able to identify that while we were still in a position to rectify it. And we actually ended up supplementing that from some food that was in cold storage from some past North Pole expeditions that had also run into their own logistical obstacles. So if you're recognizing a theme here, getting up this far north is actually quite challenging. So extrapolate that out to you know, traveling to Mars, and you can kind of see the why people are thinking about this now, even if we may still be a decade or two out from those first potential crewed missions to Mars. So we finally arrived to Resolute June 27th, a few days late after some weather-related delays. And we had basically missed our window to land at FMARS. It was surrounded by rapidly melting snow. There wasn't enough snow to be able to land the plane on skis, and the snow hadn't melted enough for us to land without the plane getting stuck in mud, basically. So looking at this again, from the lens of a Mars mission, it's the equivalent of arriving at Mars during a global dust storm. You might be able to try and plan around that as best as you can, but even if you try to plan outside of the typical dust storm season, which Mars has, you may still arrive with unfavorable conditions to land, and you may have to wait, and you may have to then adapt your planned mission to meet those constraints that you're encountering. And this has historically happened. Mariner 9, which I believe was the first mission to actually orbit Mars, had to wait 3 months before it was actually able to get a decent photo of the surface, because when it arrived, the planet was in the middle of a dust storm, and it took that long for the dust to filter out of the atmosphere. So, things happen even here on Earth, and you work with the conditions that you're in, and that was when we were able to identify that food shortage. We were able to resolve that. Anastasia was working through some customs issues coming in from Russia. And so she was able to ultimately join us before we went to FMARS. So it all ended up working out in the end. But we did end up arriving 2.5 weeks late. We did have an opportunity during that delay to try to land at FMARS, and it really just kind of cemented why we were waiting it out. You can see a lot of standing water behind the hab, and then just this nice glare from all the water flowing across the surface and just creating this really muddy, mucky surface. And actually, we didn't land here coming in, but this is actually where the airplane landed to take us out. So it really was just very unfavorable for us to arrive. But we were able to take photos of FMARS. We were the first crew to go to FMARS in 3 years at that point. I think the last mission was in 2014 or 2013 as a refit to kind of resupply the station. But even then, we didn't know what the condition of some of the equipment that was being stored outside was. And so we were actually able to get some high enough resolution photos of the ATVs that were parked outside to have a rough idea of, are the tires inflated? Do we need to bring extra equipment with us that we weren't originally planning on? So thinking of this as, a satellite reconnaissance of the landing site prior to arriving and really knowing what we were up against. So having that information at your disposal in a Mars mission is huge. So we finally arrived at FMARS after much ado. We arrived over the span of 2 different flights on July 15th and 16th. We spent the first 4 days arriving there, getting the station cleaned and ready for the mission. So to the credit of the original design and construction of FMARS, it is built to function like a spacecraft. It is very well sealed off. And despite having the windows blacked out, it can get very humid in there. And so after sitting idle for several years, there's a lot of cleaning to do, from mold buildup and that sort of thing. So there was a very deep cleaning process of using bleach, baking soda, making sure that this place was just even habitable. And we did it. We were able to flip the station 4 days, got it cleaned up and in functioning order. We were able to take stock of some of the food that was left over from previous missions, determining what was still usable at that point. And then we finally entered into SIM on July 20th, which appropriately enough is Space Day, to commemorate the Apollo 11 landing on the moon. So what's it like to live in Mars Research Station? So FMARS is about 2 stories tall, about 25 feet in diameter. There is a lab space on the first deck. So in this image, this diagram on below on the left, so there's 2 different airlocks that we move through. Basically the primary airlock where we would move in and out, and then the secondary airlock, which served as the engineering airlock, and also where we since it was closer to where we had our trash and generator, that was where we moved equipment in and out of the hab. Little bathroom and shower, workbench. Then you move up the stairs into the living space on the second floor. Everybody has their own stateroom. They're very small, but functional enough. You have your own private crew quarters that you can live in. And then you have a little kitchenette and then just common area and workstation. And then in the image above, you can see, I mean, there's certainly, it's definitely not a mansion by any means, but you're also not on top of other people. So there was room to move about. And, once you took the site or both floors into account, there were opportunities that you could break away and have some privacy if you needed that. Did have a little training bike there, which looked out across the Houghton Impact Crater, which is where the station is situated. So I think as Anastasia once put it, it's the best gym view that you can imagine. Where else can you work out and be looking out over a 20-kilometer wide impact crater? So a lot of fun. And then this was an image that Yusuke put together, kind of a fun take on each of our living quarters, and kind of give you an idea of, they're very small, but it works, especially when you're only there for a handful of months. So another frequent question that we get is, what did we eat while we were there? Well, we wanted to keep this true to the operational consistency of the mission. And so we really focused on using shelf-stable ingredients. Anastasia actually brought some Russian space food for us to sample throughout the mission that we had. I think we actually had enough. We were able to eat Russian space food twice a week for an entire meal just on that, on its own. And we were able to provide some feedback on some recipes that they had. But the rest of the ingredients that we had were shelf-stable. We were able to bake bread. This was my take at a taco night, using some of the Spam and some homemade tortillas, or pita bread. And then Alexandre was making some crepes for my birthday, which we ended up celebrating while I was out there. So definitely one of the more memorable birthdays that I've had. But, we really came together around the dinner table. It was a time for us to really relax, even if it was in the middle of the day having lunch. We really tried to get everybody in there and just have that sense of community, be able to set work down for a little bit, even if we're talking about plans for what we want to do for the rest of the day, but just being able to spend that time together. And I think that really helped with crew cohesion. And that's actually something that's been found on a number of the other shorter missions at MDRS, is that food and just mealtime is really critical in community building and building crew cohesion. So a little bit then about field science. What were we doing out there? So this was operational analog. We wanted to measure what was the science return that we could get from the mission. So we had very similar studies that were tailored to the environments that they're in. I mean, when you're looking at geology in Utah versus the Canadian Arctic, they're not directly comparable from the start, but you can design studies that are following similar procedural lines that can help you to gauge, the effectiveness of being able to conduct research in sim in those types of environments. So from the geological standpoint, John was interested in looking for stromatolites and gypsum. Stromatolites being these fossils that are some of the earliest life forms on Earth that I'll talk about a little bit more here in a minute. And then gypsum, which is hypothesized to be a potential host for, I think it's halophiles, in terms of being able to host potential life on Mars. And then my research was mostly focused on looking at pattern ground and the periglacial environment that we were in. And then John and I both worked jointly on a meltwater streak study that I'll talk about as well. Biology is a little bit out of my wheelhouse, so I won't even try to jump into that. But Suffice to say, they were actually able to do a consistent study across both sites, looking for and cataloging specimens of lichens, hypoliths, and halophiles, as well as local plant species. So the biology crew was actually kind of carrying the team on this one in terms of being able to do a study that we were really able to draw direct comparisons between both research facilities. And then the human factors study that we were doing at both sites was the twin EVA study. And what we wanted to test were a couple of different things. One was what's the difference in productivity between suited and unsuited EVAs? And then what was the difference in productivity based on the environment? So were crews more productive in Utah, or were they more productive in the high Arctic? And I think I don't think the difference between Utah and the Canadian Arctic was that large, but what we actually found was that we were more productive when we were suited than when we were unsuited. And I think the reason why that was the case was when you're suited, you're really blocking out a lot of your external stimuli. So you're really focused in on the task at hand. So if you're looking at a sample or looking at measuring plant species or rocks in a certain aliquot that you have set out on the ground, you kind of have the blinders on almost with the spacesuit to where you're really focused in on that task at hand. Whereas when you're able to move freely about the surface without a spacesuit, you can more easily say, well, I have this task that I need to do, but I'm also going to go over here and do this other thing too, and kind of run off script a little bit, and you may not actually meet your planned objectives nearly as well. So interesting outcome with that. But yeah, just touching a little bit more on what John was doing. He was looking at sampling stromatolites. So these are basically fossilized bacterial mats that they're on Earth. We see these starting to appear around 3.5 to 3.8 billion years ago, which is shortly after the Earth was formed. And important note that Mars still had liquid water. We think Mars still had liquid water on the surface around 3.5 billion years ago. So if we are looking for fossils on Mars, it's very likely to come in the form of stromatolite-like fossils. So yeah, and we were actually able to find quite a lot of them on Devon Island. And then my research, which I'll talk about here kind of for the rest of the presentation, I was focused on looking at periglacial studies, looking at pattern ground and polygons, collecting in situ temperature and soil moisture measurements, and then ultimately comparing my field observations between Devon Island and data that was returned by the Phoenix mission to Mars in 2008. So this is a blended image that I threw to piece together. On the left, we have one of my study sites on Devon Island, and on the right is the Phoenix landing site on Mars. And very subdued, but kind of the hummocky mounded terrain was the pattern ground that I was focused on. And that was actually what drew scientists to the Phoenix landing site to begin with, because on Earth, when we see pattern ground and hummocky terrain like we do on Devon Island, that's an indicator of permafrost, and more specifically a permafrost process where freezing and thawing of the uppermost layer of permafrost results in the development of liquid water. And ultimately, through the course of doing this over several years, several seasons, you end up with a sorting of the rocks and the development of this hummocky terrain. And seeing that on Mars, it kind of raised some flags as far as has the climate actually been warm enough in the relatively recent past to cause the uppermost layer of buried ground ice on Mars to melt to create pattern ground. And at the time of the Phoenix mission, we didn't know that if there was even ice in the near subsurface. And so Phoenix was able to verify that. But the current conditions on Mars are not favorable to that. So there's still more work to be done which is why we continue to look at pattern ground on Earth to better understand how it's evolving now and applying that to Mars. So, as with everything on this mission, I had an original plan for my fieldwork. I was really interested in looking at some of these larger ice wedge polygons that are about 2 miles south of FMRS. It's a really good analog for some of the larger polygons that we see on Mars, example of which I have in the lower image. And then under the ideal mission duration, this study would have run for about 2 months, and I would have collected the data loggers at the end and then processed the data set. And then on a more general level, while the data loggers were doing their thing, I would go out and survey and sample other types of pattern ground in and around the hot and impact crater. What ended up happening, it rained for at least half of the time that we were there. Muddy conditions prevented us from getting down to the middle of the crater until almost the end of the mission. We realized that pretty early on, and so I had to look at a contingency plan. The other factor that I haven't really touched on yet, some of you may be thinking in the back of your mind, is we're in the Arctic. What do we do about polar bears? Well, we had a really stringent procedure for going outside, and which included having at least one crew member who wasn't wearing a spacesuit, who would be able to man a firearm, basically be on bear duty. The other big rule was if it was foggy, we couldn't go outside. We didn't want to be in a situation where the polar bear could smell or sense us and we wouldn't be able to see it. So if we had foggy conditions, our EVAs got scrubbed. And that the fog only scrubbed the EVAs a handful of times. It was usually rain that was putting quite literally a damper on our plans. And so I had to come up with a different plan of attack on this. So one of the things that we had noticed in early preparations for the mission, and it's actually been a focus of recurring interest for crews in the past, are these meltwater streaks that are occurring right below the HAB. And these are actually quite prevalent across the high Arctic. There just happen to be some right next to the HAB as well. So HAB is a little white dot there. And the slope streaks in this case are caused by snow melt generally. So you have snow melt pack, the meltwater is running down slope, it's deflecting around boulders and solifluction lobes, which are other periglacial landforms on the surface, and then it eventually kind of tapers off the further down slope you get. We get very similar landforms or features on Mars, where you have these flows moving down a slope. You see them deflecting around boulders and craters, and it's dark. It kind of looks like it could be wet dirt, or at least that was what the initial thought process was. There's also a very strong line of thinking, which I don't want to spoil the rest of my talk too much, but the line of thinking and the one I'm more inclined to believe is that these are mostly debris flows that just happen to look like liquid water flows. But the wet hypothesis is still, worth its merit. We need to explore the options on that and the implications surrounding that. But there's a number of reasons why these debris flows might form on Mars. You might have some material break loose near the origin point, and then that sets off a cascade or an avalanche of darker colored material that moves down the slope. But in areas where this occurs in the mid to high latitudes, you start to overlap with areas where there's ground ice, and the possibility that that ground ice could potentially melt briefly and have a semi-soluble solution move down slope before it evaporates into the atmosphere, sublimates into the atmosphere. So we were interested in looking at that. The other thing that's interesting about these meltwater streaks is that there's a biofilm on these. So the darkest portions of these streaks is actually the biofilm that's accumulating in areas where the water is ponding. So there are very strong astrobiological implications to this, where you have a sustained presence of water, a recurring presence of water that is sustaining this life at the end of these meltwater streaks. For the sake of my research, something that I noticed at the end of these meltwater streaks was there was patterned ground. And it's something that hadn't been identified previously, at least in terms of this correlation between the existence of pattern ground and meltwater streaks. And so I wasn't going to be able to get to my polygons. There was some pattern ground right below these interesting meltwater streaks. And so I set up my data loggers there and let them run for the month that we were out there. So this is just a simple schematic of how they were set up. I had a probe situated on the pattern ground margins. I had one in the center, and then I let them go for a month and collected the data afterwards. Due to the short time frame, I was really able to zero in on diurnal variations, looking at temperature changes between the day and night, and then comparing that to the gradually increasing temperature as we were there towards the end of the summer. And then also looking at soil moisture content, which first glance, like Paul, it's a bunch of flat lines. Actually pretty significant because those flat lines are right around what we would predict the saturation threshold to be for these material, or for the sand and gravel matrix that these were deployed in. So they started off relatively low, and then we got a rain event, and that totally saturated them, and they stayed saturated for the remainder of the mission. So really just hit home the point. These are very water dependent features, at least as we understand them on Earth. And if they're water dependent on Mars, then that really inform us on what the past climate conditions could be on Mars, if we're going with that formation hypothesis. We wanted to get into an argument. There's dry formation hypotheses, which I think are actually quite valid. But if you're going the wet route, you have to have conditions that can sustain this level of saturation. So very interesting results. Even though it was only a month-long study, I was able to get some good measurements out of it. We eventually did make it to the polygons. It was a very happy day for me. And we've got Anastasia here. She was on bear duty, so that's why she was not wearing a spacesuit in this photo. But again, to hit home the role that water plays in this, there's a puddle of ponding water there, and more ponding water here in some of these troughs in between the polygons. So to wrap this all up, what were the lessons learned? So in terms of science return, I think the biggest thing that was highlighted through this for me is how do you handle the lost time on the surface due to whether it's a weather delay, an engineering delay, any type of mission delay that you can imagine. How do you handle that lost time? And so more importantly, how do you design your science objectives to accommodate the likelihood that things may not go totally to plan? Even if the mission goes off flawlessly from an engineering standpoint, you don't have any delays in getting to Mars, you're going to arrive there, and there's going to be days where it's just going to be too dusty to be able to go outside. You may have a high radiation day where there's a solar flare and you have to shelter in the middle of the spacecraft for several hours or a couple of days until the radiation passes through, and that's time lost. How are you going to make that up, or how do you design your studies to accommodate that type of delay? Another thing that we learned was that busy astronauts are happy astronauts. Don't want to drive home an unhealthy work ethic, but truly having meaningful daily research that you can be engaged with is key, especially during the period transiting to and from Mars. Once you're there, it's easy enough. You're on a brand new world. You're doing new things every day. But really keeping the crew engaged is key, but rest is also important. Taking time off, really just appreciating where you are, and just being able to take that in is also key. Automate engineering tasks as much as possible. We spend at least half of each day while we were at FMRS doing engineering tasks. I didn't jump into it too much, but we had to fetch our water every day from a nearby stream. Then we had to treat the water so that it was safe for us to drink. We had to burn all of our human waste, all of our garbage. That altogether took about half of the day. And then it was the other half that you were able to spend on your science activities. That was something that we didn't have to do in Utah because a lot of those supplies were taken care of for us. So there was a reduction in science return in that regard between Utah and the high Arctic. Some other things that we were thinking about while we were there and kind of interacting with some of these different variables was just the importance of in situ resource utilization, or ISRU, extracting water, breathable air, and fuel from the atmosphere and other local resources wherever possible. That not only reduces the weight that you're having to bring to Mars, it also creates a more sustainable presence for you while you're there, and a more reliable flow of resources throughout the mission. And then, good friend, reduce, reuse, recycle. Reduce your energy consumption where you can. Reuse human, organic waste, any type of waste for compost, and then recycle wastewater into either drinking water or fuel. And this is really just kind of more of a shout out to the design architecture that this is based off of. This is based on Mars Direct, which was really kind of evangelized by Robert Zubrin, who's the president of the Mars Society, and it really focuses in on staging habitat and mission hardware prior to crew arrival, but also keeping it very simple. So you don't have to have a huge sprawling Mars base for the very first mission. You can design something that fits on top of an existing rocket, your tuna can, as sometimes it's called, and launching that and landing it on the surface. And that's plenty sufficient for the first handful of crews. And then you build from there. You can make them modular to where they can connect to each other. And then you build your base from there. Watch the video. So I'll go ahead and open it up for questions. Thanks for giving me the opportunity to talk about this.
Thank you very much, Paul. That's great.
Yes, thank you so much, Paul. Fantastic. And I'll go ahead and ask a question while Scott also gets like all the questions from all the social media aspects and channels that people can post questions to. So I'll open it up with my question then is, were you able to know like how heavy your suits were or have training on all the different components of your suits?
Like prior to getting out there? We actually had a couple of different spacesuit models, and I'll back it up here to it's a photo of Joe sampling some rocks. So the FMRS spacesuits they actually go back to the very first ones they brought up there. I think, or maybe it's the second generation. So I mean, they're pretty basic in terms of kind of a simulated spacesuit design. They're basically a heavy canvas material for the basically the body of the suit. The helmets are a plexiglass like fishbowl, and then the backpacks are essentially just a fan unit that helps circulate air through the helmet so that you can cycle out the CO2. We functionally, the spacesuits at MDRS worked the same way. They were a little bit more advanced. The drawback to the canvas, and this is why the rain was such a showstopper for us, if that got wet, there was no way to get those spacesuits dry again. And then they would get weighed down and weigh even more than they did. They actually weren't that bulky or cumbersome. I think probably the worst thing is that the helmets tended to fog up quite a bit. So if you were really physically exerting yourself, that could be a problem. And if you were in sim, you just kind of had to deal with it. There were we tried putting like desiccants in there to try and help pull out the moisture a little bit. And that helped to some extent, but definitely envious of NASA grade spacesuits that have that problem a little bit more under control than ours did.
Oh, goodness gracious.
Interesting. I'm curious, Elon Musk makes claims of getting us to Mars in a relatively short time. And, I'm curious how much interaction this Mars organization and SpaceX has, if any kind of collaboration.
Yeah, so Elon's been a big supporter of the Mars Society over the years. Actually, I think the observatory that they have at MDRS is the Musk Observatory. So he's definitely recognized that value and quite early on too, in helping make it all work. I can't speak to how what that looks like today, but no, I mean I think a lot of his approach is kind of modeled on a similar thread. I mean, really trying to get to Mars under the most efficient way possible, whether that's through Dragon or Starship. I think he's kind of following that same vein. Keep it simple early on, then you can build your cities from there.
Right. And I'm curious too, for the selection process of people that would take part in something like this, is what kind of psychological testing or evaluation is made for the participants before they're even considered?
Yeah, absolutely. So for this, I applied when this was under the original name of the Mars Arctic 365 mission before it got scaled back to the Mars 160. So I was applying to what I thought was going to be a year-long simulation in the Arctic. I think during that call, which was, gosh, this was way back in 2013 now, I think they had around 300, 400 applicants. We submitted our applications, kind of a research plan, and they down selected based off of that. The second round was sending in a video interview, answering some questions. And then the final round was actually putting us in sim at MDRS end of 2014. And they had 3 different crews with finalists, and then they selected it based off of that. And actually what they ended up doing is they ended up selecting crews rather than individuals, just based off of crew cohesion. But through the course of that, both at MDRS as well as when we were in FMRS, we were given a variety of different psychological tests to take, both to gauge our mental well-being while we were out there, but also crew compatibility and chemistry. And those were actually studies that were designed by a Russian institute that designs similar experiments for astronauts on the space station. So, yeah.
Very interesting. We have some questions from the audience. Harold Locke, I think you spoke to this a little bit in your presentation, but Harold Locke wants to know, does the simulation include mining oxygen from the surface of Mars?
So in the case of our simulation, it did not. So with both MDRS and FMARS, I mean, even with FMARS being a little bit better sealed than MDRS, we're still getting ambient air from the atmosphere. So, I mean, anytime we're opening the doors and there's enough cracks, I mean, the air is exchanged frequently. MDRS actually, I think, has a proper ventilation system on it. But yeah, that being said, I do know MDRS has run some in situ resource utilization studies to try and manufacture their own oxygen for use.
Interesting. There's a number of people complimenting you on your fascinating presentation. When we get down to the next question here, let's see, we're looking at Cameron Gillis is asking, what was your most rewarding discovery? Also, what was your biggest lesson learned?
Oh, man. I think the biggest lesson learned was just having the flexibility in designing your schedule and you're designing your the research that you're conducting. I had to probably change mine more than others just because I was looking to go to specific locations that were a little bit far flung. But being able to adapt that while I was there, not being so deeply rooted, and also I think designing a study that lent itself to that level of flexibility. Because ultimately, I mean, this is also factoring into my PhD dissertation as well. So there are, some high stakes to it, but being able to, recognize when something isn't going to work and finding a new set of questions that you can address. In terms of biggest discovery, Gosh, I mean, probably just the data set that I was able to collect, and really actually having quantitative data to point to and say, hey, this pattern ground, we see it all across the surface of Mars, and just recognizing that at least the terrestrial variety is extremely water dependent. And if we're going to argue that the pattern ground on Mars is also dependent or extremely dependent on liquid water, then really have to understand the processes that are leading up to that, because Mars today cannot support that type of process.
Okay. Pekka Hautala out of Stockholm, Sweden, is asking, what would happen if Perseverance's samples shows signs, early signs of life, and I'll add to it. And what if we did find some form of life on Mars? Do we do we cancel all plans to try to colonize Mars? Do we try to speed things up to go and check it out firsthand? What have those kinds of questions been asked, and have they been kind of scenarios played out?
I think anybody who's looking seriously at Mars exploration has asked themselves that at one point or another. Should say, I mean, Perseverance is explicitly looking for signs of life, and it's the best suited spacecraft to do that since Viking, and it's leagues better than Viking was able to in the 70s. So I guess there's two possibilities to that. One is finding fossilized life, but no evidence of current life, which is extremely exciting in its own regard, because that tells the story of two separate Genesis stories that have occurred in our own solar system. And I think that would create added impetus to go to Mars to study that in greater detail, especially if there's no sign that life is present on the surface today. On the flip side, if that's a little bit more of an ambiguous conclusion that there could maybe be life, it was around relatively recently, then that might be, at least for space agencies, that may be kind of give them pause as far as how they're approaching it. NASA in particular is very stringent on planetary protection procedures. That would probably either put a pause on surface missions for a time being, or having us go through a more rigorous process to build and send craft there. It would probably slow down the human space program a little bit. Maybe not entirely.
Right, right. Martin Eastburn is asking, did you find any volcanic material up there?
Did not, although I should say there are some areas, actually, no, that's a lie. We did. There are bentonitic hills surrounding there. We generally tried to avoid those because it can get extremely muddy when wet. So I only trekked across it once. So found it, didn't really sample it, didn't really spend a whole lot of time there.
Okay.
But yeah, those are from prehistoric ash deposits going back several hundred million years.
Sure. Chris Larson is asking, what was your biggest personal challenge while you were there?
I think circling back around to my research, I mean, I was really focused in on making that work while I was out there. The biggest challenge in doing that and trying to correspond with my PhD advisor, as well as some other collaborators back home, is that we were on a time delay, and we were only connected to the internet for maybe an hour every day. It was over a satellite internet connection.
Mm-hmm.
So it was through whatever you could send out through an email. So it was very slow to get feedback, and really fostered a pretty high level of independence, and making sure that, I'm thinking through everything, as thoroughly as I need to before making a decision, because that feedback wasn't always going to be instantaneous. And that's by design too. I mean, astronauts on Mars are going to have the same types of challenges with, at a minimum, a 20-minute, delay in terms of communication. I mean, it would probably extend up to 40 minutes if it's, round trip. So
Right.
you have to have that level of independence.
Right. Andrea Villarreal is I'll rephrase the question a little bit. But basically the question is how did you, what inspired you to get involved in planetary exploration and science, to get you to where you are today?
Yeah. So my first, I guess, exposure to space flight, space exploration was doing a rocketry project when I was in 6th grade. I don't think I really made a decision to take that on as a career path until the Spirit and Opportunity missions back in the early 2000s. And that was, I followed them quite religiously through a good portion of middle school and into high school. And my journey actually started in aerospace engineering because everyone that I was talking to, it's like, well, I'm interested in space. What do I do to work in that? And they're like, well, you need to be an engineer. And so that's the journey that I started on. And after a couple of years, I was just having a hard time making that click and work for me. And it was around the same time that I realized, you can do just about anything that's even adjacent to space exploration and make that work as a career. And so I switched my majors to geology with the plan in that moment of switching to geology that I would eventually go on to get a master's or a PhD in planetary science. Took me a little bit to get there, but that was kind of the track. I decided to apply to the Mars Arctic 365 simulation that turned into this. That it would have been the year after I graduated from my undergrad and was kind of in between that and grad school. So I was doing this sight unseen as far as what I was even going to be doing for my PhD. And so it really kind of helped shape that rather fortuitously.
That's cool. That's cool. Would you do it again?
Yeah.
You definitely. Yeah.
Yeah, I would definitely do it again, especially if it's with the same crew. I think I saw there was a call for volunteers to do some mission simulations out at high seas. That I probably won't do it just because I need to finish my PhD, but I was like, it's tempting. But they're fun. I would do it again.
Okay. All right. Well, I think that covers our questions from the audience. And you answered a few of my questions too, Paul. I'm beside myself that you're right here in Springdale, so it's great.
Yeah.
And hope to get to meet you in person here at one point.
That'd be great.
Any other questions, Caitlin, or anything that you want to add or to talk about the next program?
I'm just so excited. This is such an amazing project and an amazing experience. I'm glad that the Mars Society, or just now private companies, I'm sure, are going to start to step in soon and kind of do like their own versions of simulations like this in the future. It's going to truly open up a whole new level of opportunities, specifically for like grad students and early career folks. We definitely need more programs like this. So this is so exciting that you were able to tell us about your adventures this evening. So thank you so much, Paul, and good luck with the rest of your PhD adventure that is still continuing as well. So so that's also really exciting too, with all the pattern ground work that you're doing with Mars.
Thank you.
I guess we'll end this with one last question. This is from an 11-year-old student that's watching. And the question is what advice do you give me for someone that would like to study space?
Absolutely. Definitely. Especially at your age, follow your passion wherever it goes. Use the internet to your advantage. Any topic that you're interested in, read up on that. Check out books from the library. Really, use this time while you're, still going through grade school to, explore the range of interests. Also, continuing to do well, your coursework. Math and science, I mean, are the usual answers. And I mean, for a reason, that's really the foundation of anything that you jump into, especially as we're rapidly moving forward with technology. If you have an opportunity to take any computer science, programming types of courses, even just getting a very basic foundation on that is huge. I'm straddling that generation where there was a lot of this technology when I was growing up, but not the emphasis on the programming. And I'm having to play catch up on the programming now. So if you have an opportunity to do that before school.
Right. Right. Any other words of wisdom, Caitlin?
Oh goodness, I think Paul said it perfectly, especially the catching up with the technology part. I know that all too well. Yeah, we're definitely in that same cut from the same cloth there of the technology has grown so much now. So who knows what technology astronauts on like the moon and Mars are going to have.
Oh my goodness.
It's going to be astounding to not only get that technology there, but then train the astronauts when here we are trying to train ourselves how to use the technology here on Earth. So it's going to get interesting to say the least, though.
Yeah,
very cool, very interesting. You know, something comes to mind. I had a conversation with Buzz Aldrin about exploration, you know, beyond our solar system. And he said that he felt fairly confident that it would happen, but it would probably be artificially intelligent, you know, beings that would do that. Okay. And so I'm just, I'm curious as AI accelerates, you know, to what level it'll be used when we finally do get to Mars and colonize. You know, so I can imagine as far as life support systems and you know, sequencing through, you know, backup plans that could be done in case there's an emergency of some sort. I would see that AI would be of huge benefit. So,
absolutely,
yeah. Anyhow, well, you guys, thank you to the audience. You guys were wonderful. Some great questions. Caitlin, thank you for bringing Paul here. Paul, it was absolutely fascinating. You know, I am now well convinced that Arkansas is a hotbed of planetary scientists and space exploration type people, and I need to know more of them. So,
gotta watch out for Northwest
far and wide to get people to be on our programs, and many of them have obliged. But it's cool to know that many are right here in my own backyard. So. Very cool. All right. Well, that's it for tonight. Remember on Saturday that we have. It is May 15th is Astronomy Day, International Astronomy Day, and the Royal Astronomical Society of Canada, the Montreal chapter, is the official co-host of this program. They've already got a great lineup of speakers, and we were able to invite Doug, why am I having a space out on his last name right now? But the gentleman that actually started Astronomy Day is going to be on the program as well. So, you know, I'm very, very excited about that. And that will start at 6 p.m. Central here on Saturday evening. So we hope that you join us. And we'll be talking more about the speakers and the activities going on that special day. So Astronomy Day is like Christmas for astronomers. So celebrate it. And take care. And thanks very much, you guys. Take care.
Thank you. And thank you again, Paul.
My pleasure. Thanks for having me.
Bye-bye.
Bye.
Hello, everybody. This is Scott Roberts from Explore Scientific, and today I want to talk about the world-famous Galileo Telescope Kit. This is a kit that you assemble by yourself. You'll learn how optics work by assembling the objective lens and also the eyepiece. And there's two different eyepieces that are in this. The 25 power, 20 millimeter eyepiece, but it also comes with this very clever little device here that works both as a Barlow lens that will double the magnification of this eyepiece, making it 50 power, or it can be used also as a Galilean eyepiece, which gives 17 power to the telescope. This is what Galileo virtually saw through his own telescope. So you can have that same experience that Galileo had looking at the moon, looking at Saturn's rings, looking at Jupiter. It is a telescope that was designed for the International Year of Astronomy in 2009, and it's a fantastic kit, both for child and adult, to learn how a telescope works. And so if you get the telescope like this, you can either have it on a stand like this, you can hand hold it like a pirate's glass, or on the bottom here we have a threaded hole here that you can put it on a camera tripod. Very versatile, very rugged, and a lot of fun, all from Explore Scientific.